All right, let's just do a picture of a for loop, just for completeness. Did you do flow charting in 120?
Yes.
Okay, cool. Sometimes we go over that, sometimes not. So let's just look at this for loop. I'll change the lighting here. Better. So for I equals 0, I less than 10, I plus plus, and we'll just do some print statement inside here. All right, so what's the first thing that happens when we're about to execute this loop?
We set I to 0.
We set I to 0, so it says I equals 0. All right, and what's the next thing?
Check to see if I is less than 10.
Check to see if I is less than 10. And if it is, we'll do our print. And we'll do whatever else is in the body of this. And then what's the final thing we do? I plus plus. I keep abbreviating. Let's just do I equals I plus 1. So we do I equals I plus 1. And then we go back up to the spot where we check to see if I was less than 10. And if I is no longer less than 10, then we come down here and we just go on to whatever comes after the for loop. That's the basic flow of a for statement. And if we wanted to generalize that, it might look like this. For some initialization, some test, and some, what should we call this? Some end statement. And what we want to do in here is whatever the body of the for loop is. So if we wanted a flow chart for this, exactly the same thing. First thing we do is our initialization. And then we check our test. And if the result of this test is true, or yes, then we do the body of the for loop. And we do our end statement. And then we go back up to the test. And if the result of the test is no or false, then we come out and we exit the loop. So that's basic for statement. How many people here know anything about go-tos? Or have heard the word go-to? So earlier languages, assembly language, right, the stuff that's close to the machine level, Fortran was one of the first widely used languages. BASIC was one of the very first programming languages. These all had statements that were called go-to. And go-to would let you say, okay, instead of executing this next line of code, I want to go to some other section of code. And you could put a label somewhere and say, okay, I'm going to call this section of code, you know, my cool function. And somewhere I could say, go to my cool function. And instead of doing the next instruction after the go to, it would jump down to this other set of code. And then it could execute some things, and then you could have another go to which says, go to this section of code, right? And using go-tos and if statements, we can make a for loop like this. It would be pretty easy. We put a label up here. We'd do this test, and we'd say, if this test is not true, then go to, we'd put some label down here. Otherwise, we do the body, we do the end state, and then we'd say go to whatever we put the label at the top of the loop, right? And go-tos were, an essential part of early programming languages, and assembly language machine codes still have go-tos. C actually still has a go-to statement, but don't ever use it if you're going to show your code to other people. You can use it with the shades drawn and the doors locked. So go-to started getting a bum rap in the 70s and especially in the 80s. And here's what was happening. Here's one of the things that was happening was people had been developing code for years. And in some cases, one set of code may have existed for 20 years. So gas company started using computers and they started writing code to track customer billing. And they kept adding things to the code. And there's new taxes, so they add some tax handling things to it. And now they start letting people pay their average gas bill all at once up front. And then they give them a discount, right? And so you used to have a set of code, that did like our checkout program. Start here, do these things, and you're done. And now you needed to write some more code. Well, unlike C, some of these earlier languages, you had to put line numbers on each statement. So this would be statement 10, this would be statement 15, this would be statement 20. And if you tried to put too many things between statement 10 and 15, it wasn't possible, because you could only use statements 11, 12, 13, and 14. And if you needed to put 10 statements in there, what would you do? You would say go to, and you'd jump over somewhere else, do your 20 statements, and then you'd say go to, and jump back up here. Well, that's not too bad once or twice, but after 20 years of this, you get what was called spaghetti code. Because if you tried to draw a flow chart, it was just arrows pointing everywhere. And right, spaghetti, you pull on one strand, you have no idea what it's connected to. And this was a nightmare to deal with. Okay, people started doing studies and reporting things like 90% of the total cost of a piece of software is maintenance. 10% is the original writing of it, paying the programmer to write and debug the code. And then 90% of the final cost is just maintaining it over time. And part of the problem with maintaining it was that the code was sloppy, right? And so there were all kinds of books like go-to is considered harmful and stuff like this. And it became this torch and pitchfork kind of thing where people said, get rid of the go-tos, they're evil, they're destroying us. And so languages were developed that did not have go-tos, but they had things like this, right? It's still doing a go-to, but it's doing it in a very controlled way. And there's no way that this is the same as this, right? Where we've also got this branching off over here and doing some things. And then this is branching off here and doing some things. And this is branching off here and doing some things, and then branching off somewhere else, and then coming back, right? So there's spaghetti code, all sort of tangled up. This has still got branches, but it's in a very controlled way. So this was called structured programming. And people started teaching structured programming. So I was an undergrad when structured programming was all the rage, and got it, forced on me. But one of my teachers told me an anecdote. There was an interview with a blind programmer, okay, completely blind, could not see with his eyes. And the interviewer was talking to him, how long you've been programming, number of years, right? What's the longest program that you've ever developed? About 10,000 lines. And this was astounding, a 10,000 line program. And how do you do that? Well, he had somebody who would read the code to him, and he would say what should be changed, the person would make the changes, right? 10,000 lines without being able to see it. And he said, yeah, but there's one caveat to that. If there's a go-to statement that goes to a section of code I haven't already heard, I'm lost. If it goes back to a section of code that I've already gone through, it's fine, right? So that's kind of this idea. You're going back to somewhere that you've already gone through once, right? And this is going to the next statement. It's kind of not really a go-to. And so this is one of the anecdotes that people used when they talked about structured programming. So structured programming meant you had things like for loops and while loops and if statements. And so this is what we have today. And it works well, but you know, once you compile it and you turn it into assembly language, it's back to go-tos. Right? But it's written by the computer, it's written by the compiler, and it's read by the CPU. We don't usually interact with it. So it's okay. All right, so there's another kind of loop, which is a while loop. While loops are easier than for loops. So while parentheses some condition, and if that condition is true, execute the body, and then go back up and check the condition again. As soon as the condition is false, leave your whole while loop and just come down to whatever comes next. And that's a pretty simple flow chart. See if your test is true. If it is, do the body and go back up to the top. If your test fails, leave your loop. And this looks an awful lot like this, right? This was our for loop, this is our while loop. There's a check on a test. If the answer is yes, it goes down and it does some stuff and comes back up to the test. If the answer is no, it comes down here to whatever comes after the loop. The for loop has an extra initialization in the top. And it's got an extra statement here at the end of the body. But it's the same structure, right? And we can make a for loop out of a while loop. So when I teach 120, I don't teach for statements. I only teach while statements. But let me clean this up a little. All right, so there's our original for loop. Prints out 10 times. We could make this a while loop. So what do we want to do? Well, first we need to do our initialization ourselves, which was to set I equal to 0. And then we're going to do the same test, but we're going to put that test inside our while statement. So we're going to say while I is less than 10. And what we're going to do in the body is print out hello, but we're going to put this end statement in the body ourselves. The end statement was I equals I plus 1, so we're just going to add that to the bottom of our loop. This will do exactly the same thing as the for loop. Which one do you use? Personal preference. Sometimes one is sort of more natural than the other. Here, I really just want to execute that statement 10 times. That's a good case for a for loop. In particular, I want to execute it 10 times and I want to increase the value of I from 0 to 9. That really screams out for a for loop, right? But if nobody said you have to use a for loop, use a while loop. Okay, let me show you an example of where we might use a while loop. Suppose we want to put a secret password on your program. You're going to run the program and it's going to give you a secret message, but before it does that you have to put in the right password. And if you get the password wrong, it's just going to say, nope, wrong, try again, try again, try again. So I'm thinking something like this. Start of the program. Ask for the password. And then, is the password wrong? And if the password's wrong, I'm going to ask for the password again. And if it's wrong, I'm going to ask for the password again, and so on. If the password's not wrong, I'm going to come down here, and I'm going to print the secret message. And then we're done. Okay, this looks exactly like a while loop. Ask for the password, and while the password is wrong, ask for the password again. When I come out of this loop, it must be the password was correct, and now I can go on and I can do whatever I want, print out the secret message. And this you can't really do with a for loop, because I don't know how many times I want to loop here. Right? It's not a matter of incrementing something and waiting until it's a certain size. It's really some condition here that I want to check. So let's try this. So we'll ask them to enter the password. I'll call this password instead of I. So the password's an integer. All right, what should our secret password be? What's our 49? Okay, don't tell anyone. So while the password is not equal to 49, we're going to say wrong, enter the password, and we're going to ask for the password again. And then we'll just print out the secret message. I'll add some comments in here. So this is my initial prompt. This is the user's first try. As long as the password is incorrect, keep trying. And then down here, the user finally entered the correct password. Does that look reasonable? So enter the password 23, 48, 50, 49. There you go.
How'd you make it alphanumeric?
How would you make it alphanumeric? Oh, that gets really tricky really fast. So we have to use what's called a string, which is an array of characters. And that needs to get into characters, and needs to get into arrays, and it needs to get a little bit into pointers. So that'll come in a few weeks. And it would just be a different type of variable besides an int. Just making sense? So that's a while loop. Now if I had made this an if, what would it do?
It would ask the one time if they entered.
Mm-hmm.
And then we'll keep moving. Return 0.
So it'll say enter the password.
Oh, actually,
It'll let me put in a password. And if my password is correct, it'll say secret message as before. If my password's incorrect, it'll say wrong, enter the password, ask me again, and then it basically gets down here, which is the end of the if statement, and it goes on and it prints secret message. Doesn't loop, right? So if you want it to go back and keep doing something, you want some kind of loop. All right, let me back up and look at ifs. Again, let's not loop for passwords. Let's just give them one shot at getting the password right. Okay. So we're going to ask them for the password. We're going to let them type in the password. We're going to say if the password's equal to 49. We're going to say congratulations. So if they put in the right password, we're going to say congratulations. If they don't put in the right password, what do we want to do? Well, we want to do something. We want to tell them, you don't know the password, goodbye. So we could do this. Password's 49, say congratulations. If the password's not 49, say sorry, goodbye. So enter the password 23, sorry, goodbye. Enter the password 49, congratulations. This kind of thing happens a lot. If the password's 49, do something. If it's not 49, do something else. There's a different way to write this. We can use what's called an else statement. And so an else statement looks like this. The password's 49, say this. Otherwise, else, say sorry. So password's 23, sorry. Password 49, congratulations. And I usually would do it like that. So this is called an if-then-else statement. The word then doesn't appear, but the curly bracket after PW equals 49 we can think of as then. Password is 49, then print congratulations, else print sorry. All right, one more embellishment on this. You had asked about multiple conditions. Suppose we want to have two passwords, 49, but we also want to have 42 be another password. So we could do the following. If password equals 49, or, and the way we say or is by putting two pipes, or password equals 42. And I put my condition PW equals 49, I put that in parentheses just to sort of break it apart from the other pieces. So if password is 49 or password is 42, then say congratulations. So 23 is wrong, 42 is correct, 49 is correct. And there's lots of ways we could do this. We could say if password equals 49, print congratulations. Else, if password equals 42, print congratulations. Else, print sorry. So we could have an if with two else statements. But here we're using a compound condition, a condition that checks two things. Let me show you one other thing. This is really, really, really advanced. Let me comment this out. This is what we were doing. Actually, let me comment out all of this. Okay, back to 1Password. I could also write my statement like this. If the password is not 49, say sorry, else say congratulations. And that's going to work equally well, right? Just 1Password. All right, 23 is bad, 49 is good. Exactly the same behavior, but a totally different statement from what we originally had. If the password's not 49, that's the incorrect password. Otherwise, it's the correct password. Okay, how would we add two passwords in this case? What might our if condition be? And we might try that if password is not 49 or password is not 42. And 49 no longer works. And 42 no longer works. And nothing works. So that's not quite right. But forget about the code. Just think about it logically.
Does that come after else?
We can do it just by putting the right thing on this one line, the if part.
You can't use it. You can't use an or.
Can't use an or.
If it's not 49 and it's not 49.
Who said and? And.
Yeah.
If the password is not 49 and the password is not 42, then they got the password wrong. So this becomes an and. And the way we do and is with two ampersands. So or is two pipes, and is two ampersands. If the password is not 49 and also the password is not 42, then we can absolutely say the password's wrong. All right, and I mention this because you're going to see this again. If you've done 250, you've seen this. If you haven't, you'll see it in 250. If you do the computer science sequence, you'll see it in CSE 215, discrete structures, and we'll bump into it in coding a lot. This is something called De Morgan's theorem. And it's basically a way to change between ors and ands, and change between things being true and things being false. So don't worry if that's weird. It's supposed to be weird. But we're getting to the weird part of the night. So 23 is bad, 42 is good, and 49 is good. All right, questions?
How do you give the users like 3 times to enter the correct?
That's a really good question. Suppose we wanted to let them have 3 tries. One way to do it would be to have some nested if-then statements. So here's one approach. Read the password. Password equals 49. And if yes, then just go on and do whatever, right? If not, we could say read the password. Password equals 49. And if yes, go on. And if not, we could have one more try. Read the password. Is it equal to 49? And if yes, go there. And this time, if not, then we could, do our return or our end or something like that. That will work, but it's if you want to give them 10 tries, it becomes really hard to write this. So we could combine this idea with a while loop, right? We've already got a while loop which runs forever. So we've got ask for the password. If the password's wrong, then ask for the password again, go up to the top again. So now we could keep track of how many times they've done this. So we could have something like tries equals 0. And when we ask for the password, tries equals tries plus 1. And then in here we could say is tries bigger than 3? And if it is, then print a message saying they've tried too many times and exit. But to code that in C takes more machinery than we've talked about. That starts to get into something that will be called flags, where we'd want to set something inside here so that when we leave the loop, instead of printing the message, we'd say, oh, we left the loop because they tried too many times. And then at this point, we'd say, sorry, you're out of tries, and we would exit. But we can do it by putting together what we know, but it goes together in a kind of a weird way. All right, it's a great question. Other questions? So again, this is sort of about 10,000 foot view of stuff. The conditionals and the looping in particular, right, is kind of bonus material, and you'll come back to it and treat it from the beginning with Scott. But it's good to have bouncing around in your heads. Let me just tell you a story for programming, and then I'll give you your quiz, and then we're done. But a really brief story on programming, just something to keep in mind. So when I was a kid, I was really into prime numbers. Okay, I mentioned prime numbers first week. I was really into prime numbers. And I learned that there was no general way to create prime numbers. This is still true today. And if you come up with a machine, you can turn the crank and prime numbers pop out, you can destroy the world, basically. Okay, the government is terrified of this possibility. So of course I wanted to figure out how to do this. It wasn't terrifying back then, but with electronic commerce, right, it falls apart if you can produce primes. Other things fall apart. So I wanted to come up with a formula that would produce prime numbers. And I came up with all kinds of crazy formulas. And most of them, they'd work for a little while, and then there's a number that's like divisible by 3 or 5 or ends in a 0 or something, right? But I started coming up with formulas that made numbers that I was like, sure, this is it. This is the one that's, going to make me famous because it's just going to produce prime numbers. It's never been done before. What it was doing was producing numbers that were too big for me to test, but they looked kind of prime. They had lots of 7s in them, and they didn't end with a a 5. They weren't divisible by 3 because you can add up the digits. If the sum of the digits is divisible by 3, your number is not prime. They failed these simple tests, but I couldn't really test, to see if they were truly prime or not because they had like 7 or 8 digits to them. So my dad, he worked at IBM, and somehow we got talking about this one night, and I knew he worked at IBM. IBM meant computers. Computers can do things, right? Hey, Dad, is there any way that, someone at IBM can test these numbers for me? He's like, let me talk to someone. So I gave him the number on a piece of paper, and he came home the next day from work, and there were like 4 numbers written down, and if you multiplied those 4 numbers, you got the number. So it wasn't prime. It's divisible by 4 things. Huh, okay. So I came up with another magic formula. Oh, this one's going to work for sure. And gave him the number. He gave it to his friend. Came back, sheet of paper. Number was factored. Right. So the third time I did this, he came back with the factors of the number, but the person also had given him a sheet of paper. It was this weird white paper, kind of shiny, and had all these symbols on it. They were literally Greek symbols. And I'm like, what's that? And he's like, that's the program he's using to figure out if your number is prime. And I was like, whoa. So I took this into school and I showed it to my friends. We were all kind of like interested in computers, but didn't know what this was. And we worked on it for about a week, and we figured out what this program was doing. And in my brain, it was like, how is this computer telling if the number is prime? What magic is it using, We figured out what this program was doing. It was taking the number, and it was trying to divide it by 3, and then trying to divide it by 5, and then by 7, and then by 9, and by 11, and by 13. It just kept trying to divide it by different odd numbers. And if it found that it was divisible by one of these numbers, it would say it's not prime. And if it wasn't divisible by any of these numbers all the way up to the number -1, it would say the number is prime. And it blew my brain, because it wasn't using anything magic. It was doing exactly what I would do if I had the patience. Just get a calculator, start trying to divide your number by every possible number smaller than it. And I knew I didn't have to divide by even numbers, because if it was even, it wasn't prime. But I'd divide by 3 and 5 and 7, and I just looked to see if there was anything after the decimal point. It's exactly what this program did. And it just totally it shook me to my core, because it was so simple. And that really kind of set my relationship with computers from that point forward, which is there's nothing magic. It's just going to do what you ask it to do. All you got to do is figure out what to ask for, right? And if you can ask for the thing that you really want, it'll give it to you. It'll do it really quickly usually too. So it's all about figuring out how to ask that question. All right, so let me pass out a short quiz, and I'll collect these at 7:15.